Okay, so we're going to continue on with the image intensifier, and we're going to talk about influences of the image intensifier. So, flux gain, that's one of the things you're going to have to know. So it's a considerable amount of light at the output phosphor. It produces 50 to 75 times. Here's the thing, the syllabus for the states says 150 to 150, so we'll use those numbers. Considerable amount of light at the output phosphor. It produces 50 to 150 as many light photons as incoming X-rays. So just a hint here, the flux gain is usually around 50 times more. The ratio of the image of light photons at the output phosphor to the number of X-rays at the input phosphor is called flux gain. So here's your formula. Flux gain, so it's the number of output light photons over the number of input X-ray photons. So look at page 18 in your fluoro syllabus. This is all in your fluoro syllabus, so you can follow along. So flux gain for each light photon emitted from the input screen of the image intensifier tube, on average 50 light photons are emitted on the output phosphor screen. Remember that one light photon from the input screen will eject one electron from the photocathode. Remember, it was 1 to 1. This one electron will have enough kinetic energy to produce 50 light photons at the output screen. It is important to understand that the flux gain is an inherent number that each individual image intensifier tube manufacturer will indicate. So there's your flux gain again, and here's a sample problem. This problem won't be as easy as this one, so you can see your one incident X-ray coming in. Here's your input phosphor, so 1,000 light photons. Here's your photocathode, goes to 50 photoelectrons. Here's your output phosphor to 3,000 light photons. Minification gain, the ratio of the square of the diameter of the input phosphor to the square of the diameter of the output phosphor. So the output phosphor is fairly standard. In modern units, it's 2.5 centimeters. The input phosphor varies from 10 to 40 centimeters and is used to identify image intensifier tubes. So we're going to talk about the magnification here in just a minute. This is the result of the same number of electrons that were produced at a large input screen being compressed into an area of the small output screen. So a lot of the input are size 6, 9, or 12 inch. Your minification gain, here's your formula. So the input screen diameter squared over the output screen diameter squared. And there's a sample problem for you. Brightness gain is defined as the ability of the image intensifier to increase the illumination level of the image. So the increase in illumination of the image is attributed to the multiplication of light photons at the output phosphor compared to the X-rays at the input phosphor. And the image minification from the output phosphor to the input phosphor to the output phosphor, so minification gain. So here's your formula. It's actually easier to see it than try to understand it. So you have to solve for your minification gain first, multiply it by your flux gain. So the brightness gain on most image intensifiers is 5,000 to 30,000. The brightness gain deteriorates or degrades as much as 10% per year due to aging of the input and the output screen phosphors. So you have a conversion factor that measures the brightness gain. That is the ratio of the intensity of the output phosphor to the input exposure rate to the input phosphor. So there is your formula, usually measured in candelas. So going next into the beam splitter mirror. So in your syllabus, you'll see it follows along. Allow 10% of the output phosphor light image to be scanned by the Vidicon, and we're going to cover what that is next week, I believe. So 90% of the output phosphor light is to be projected towards the cine camera, the photospot camera, or directed viewing through a mirror that is found outside older generation image intensifiers. So you can see here you've got a mirror so that you can expose. I have worked on a machine like this, very old. Beam splitter mirror, the best resolution and the brightness is found at the center of the image. Yes, of course. Okay, so here we go into the magnification image intensifier tubes, how it works. So the input phosphor size changes when a higher voltage on the electrostatic focusing lenses is applied. The more the electron beam is focused. So it actually makes the input phosphor smaller. So the electrons are accelerated faster to the focal point, so it moves toward the input screen. So the focal point actually shifts towards the input screen. This causes the image to be magnified when it reaches the output phosphor. So the smaller portion of the image is enlarged to a full output window, resulting in a magnified image. So with it moving towards the input phosphor, it actually gets bigger on the output phosphor. So the center of the image has better resolution and less geometric distortion with smaller image intensifiers. So it gives a better image quality than a larger unit. 9-inch is used for larger atomic areas, and a 6-inch II is used for better image quality. So its useful area of the input phosphor is decreased while the output phosphor remains the same. The collimators are automatic to the 6-inch and reduces minification gain with fewer photoelectron incidents on the output phosphor, giving a dimmer image. So what happens is the ABC will have to kick up the MA to compensate for this decrease in brightness. So when you go from a 9-inch to a 6-inch II, what happens is your MA kicks up, which means what? More patient dose. Here's an idea. Here's a 9-inch II right here, and you can see your focal point. When we go to the 6-inch, these electrostatic lenses bring in the focal point and shifts it further back. So magnification of the image intensifiers are capable of 1.5 to 4 times magnification. The ratio of patient radiation dose is calculated using one of the formulas. So the increase in the patient radiation dose, so you take the normal mode squared divided by the magnification mode squared. And this gives you an idea using the 12-inch, 17-inch, or 25 cm II, what happens to your focal point and where it moves. And as you can see here on your output phosphor, is still the same size, which gives you that magnified image. So mag modes, the increase of radiation dose results in better image quality. Also better spatial resolution, contrast resolution, and higher patient dose. So there's a trade-off. Some of the imaging considerations that I want to talk to you about in your syllabus and in Carleton. Image quality of the image intensifier is affected by quantum model, which is also called quantum noise or scintillation, contrast, resolution, and distortion. So we're going to talk about those. Quantum model, so same thing, it's a grainy appearance in an image caused by statistical fluctuations in absorbed X-ray photons. So it's a starved image, same thing as X-ray. Model is more visible in high resolution, high contrast systems. This is when not enough photons are there to produce an image. Increasing the exposure increases the number of absorbed and remnant photons and helps reduce quantum model. So contrast. Overall contrast in the image depends on the subject contrast, detector contrast of the II and the TV camera. So the brightness between the two adjacent areas of fluoroscopic image is called intensifier contrast. Factors that diminish contrast in IIs, so the input phosphor does not absorb all photons in the X-ray beam. Some are absorbed by the output phosphor, contribute to illumination of the output phosphor, not the image formation, aka fog to film. So it's kind of the same idea. Retrograde light flow form output phosphor can diminish contrast. So output phosphor is transparent to light photons that spread within the structure before visualization detection. These produce fog and further degrade the image contrast. Resolution is the ability of the imaging system to differentiate small objects as separate images as they are positioned close together. It's measured in line pairs per millimeter. Object size and line pairs are inversely related. As the object size becomes smaller, better resolution, the spatial frequency becomes higher. A perfect system would have a modulation transfer function of 1. So that's kind of the same idea as your digital system. So your cesium iodine is approximately 4 line pairs per millimeter, where your older zinc cadmium was 1 to 2 line pairs per millimeter. So as you can see, with the newer systems, we're getting better quality, better resolution. So distortion. So electrons focusing is not uniform across the entire field of the II. electrons at the center of the unit are more accurately focused than those at the periphery. So the periphery electrons tend to flare out and they kind of go off course. Remember that divergent beam. This results in unequal magnification, which produces peripheral distortion. It's greater with larger intensifiers because the further the electron is from the center, it's more difficult to focus. Pin-cushion distortion. So it's a form of spatial distortion that warps the appearance of the image. Results of projecting the image formed on a curved input phosphor to a flat output phosphor. So as you can see, that would cause distortion. Higher magnification of the input image towards the edge of the image and reduces when mag modes are used. So blur or lag. Blur and lag. So a certain amount of time for the image to build up to actually see it on the monitor. So it takes the system time to adjust the technical factors, and when you move the II really fast, it doesn't have time to catch up with itself and apply the proper settings. So it'll show as blurring, or like you'll see the screen just kind of drag across. Vignetting. With traditional IIs, there's a loss of brightness at the peripheral of the image. The peripheral of the II, of the input phosphor, is inherently unfocused. Therefore, better resolution at the center of the II. So you can see here, it's better here than it is out here. So you can see it's a lot darker out there. Veiling glare. So internal scatter in the form of X-rays, electrons, and light can reduce the contrast of an image intensifier, usually from light being scattered, adds to the background signal and reduces the contrast on the image, and new output designs help with this issue. So you can see here we have some scatters in there. So I want you to be able to label this here. So you need to know what A is, what B, C, D, E, F, G, and we'll get to these down the road. I need you to be able to label through G. Okay, so we've covered all of that, and I'm going to leave you with this last one. If I died and went straight to hell, it would take me a week to realize I'm not in X-ray school anymore. I'm sure that's how you feel. Hang in there. You're at the downward stretch. Almost done. Stay focused.